All right, so today we are going to talk about data privacy, which is a crucial aspect of our digital lives. Data privacy refers to the protection of personal information and then the right individuals have to control how their data is collected, used, and shared. In an era where data is constantly being gathered, ensuring privacy is more important than ever. Now let's look at what's personal data in the first place. So personal data include any information that can identify a person. This could be your name, address, email, phone number, or even sensitive details like your date of birth and social security number. Any piece of information that, along or combined with other data, can trace back to you is considered personal and need protection. And different countries have laws to safeguard data privacy. For example, the General Data Protection Regulation, GDPR, General Data Protection Regulation, in the EU enforces strict guidelines on how business handle personal data, while the California Consumer Privacy Act, CCPA, grants consumers more control over their information in the US. These laws ensure that organizations collecting personal data do so responsibly. Organizations must be transparent about how they collect and use personal data. They need to obtain explicit consent before collecting data and clearly explain the purpose of data collection and provide individuals the option to opt out of data sharing. They also need to store data securely and restrict access only to authorized personnel. And in terms of individuals' rights, the people have the right to access, correct, or even request deletion of their data if it's inaccurate or no longer necessary. This ensures individuals retain control over their personal information. Unfortunately, data breaches happen when personal information is stolen or exposed, often due to cyber attacks or human errors. In such cases, companies must notify affected individuals and take steps to mitigate harm. While companies play a role in safeguarding data, individuals must also take precautions, such as using strong, unique passwords for online accounts, avoid sharing sensitive information with unknown sources, and also stay vigilant against phishing scams and cyber threats. So overall, data privacy is a shared responsibility. Governments, business, and individuals all have roles to play in ensuring that personal information remain secure. By staying informed and taking proactive steps, we can better protect our digital lives. Next, let's look at different data privacy protection techniques. So protecting personal data is a challenge, but several techniques have been developed to ensure privacy while still allowing useful data analysis. Now we will discuss three key techniques: K anonymity and data masking and differential privacy. Each of these three methods help safeguard sensitive information in different ways. So let's discuss the first technique called K anonymity. So this is to prevent individual identification. K anonymity ensures that no individual in a data set can be uniquely identified. It works by grouping people together based on shared attributes such as age, gender, and location, so that each individual is indistinguishable from at least k others in the dataset. So for example, if k in the method of k anonymity is equals to 5, this means that at least 5 people share the same characteristics, making it difficult to pinpoint a single person. This technique is commonly used in medical and census data to prevent the re-identification of individuals while still allowing researchers to analyze trends. The second technique, data masking, is to hide sensitive information. So data masking replaces sensitive information with modified but realistic looking data. The goal is to protect the original information while allowing systems to function properly. For example, instead of storing a real name, a system may replace it with a pseudonym, such as John Doe, to replace John Doe with user 123. A zip code might be replaced with a broader region to make it harder to check a specific address. Data masking is widely used in testing and development environments to prevent exposure of real user data. The third technique, which is quite popular, is called differential privacy. It's about adding noise for protection. Differential privacy takes a different approach by adding random noise to data sets. This means that even if someone tries to analyze the data, they won't be able to identify specific individuals. For example, if a dataset includes survey responses, differential privacy might slightly modify the data by adding random variations, but in a way that still preserves overall trends and insights. This technique is especially useful for large-scale data analysis in areas like social science and AI research. Each of these three techniques, k-anonymity, data masking, and differential privacy, helps protect personal data while allowing organizations to analyze information safely. By using these methods, we can balance the need for privacy with the benefits of data-driven insights. In today's world, organizations collect and analyze vast amount of data. But how can we ensure that personal information remain private while still allowing useful insight? This is where differential privacy comes in. It's a powerful technique that helps protect individual identities while maintaining the overall usefulness of data. So let's look at what's differential privacy. It's a statistical technique that adds random noise to data. This ensures that individual records can't be identified, even if someone tries to analyze or reverse engineer the data set. The key idea is that the presence or absence of single individual does not significantly change the overall results. There are two main approaches to differential privacy. One is adding noise to the data itself. Random values are added directly to individual data points before analysis. So this makes it difficult to trace data back to specific individuals. The second technique is adding noise to the analysis. Instead of altering the data, this approach introduces randomness into calculation, such as by slightly modifying the result of a machine learning model. The differential privacy is important technique because it allows organizations to share and analyze data without exposing personal details. And it prevents the re-identification of individuals in data sets. It's widely used in areas like government statistics, healthcare research, and AI training. What differential privacy? So we are going to discuss about the technical details of differential privacy in upcoming slides. Here, we just focus on some high-level discussion of differential privacy to help you gain some insights into this technique. So this technique has its limitations. It's a powerful tool, but it's not foolproof. If an attacker has access to additional external data, or if the noise added is too small, re-identification may still be possible. Striking the right balance between privacy and data accuracy is a key challenge. So differential privacy is a critical tool in data protection, and it ensures that individuals remain anonymous while organizations can still extract meaningful insights. As data privacy concern grows, techniques like this will play a major role in securing sensitive information. Next, let's look at technical details of differential privacy and how it works. Right? To understand how differential privacy works, we need to explore its key parameters. These parameters control how much noise is added and how well individual privacy is protected. The three main factors are global sensitive, F, the privacy parameter, epsilon, and the spread, B, of the Precision distribution. All right, so let's look at global sensitive. So intuitively, you can understand global sensitive. F controls how much can the data change. It measures the maximum difference that a single individual's data can make in the data sets. The larger the sensitivity, the more noise needs to be added to prevent re-identification. It's positively related to the amount of noise. Higher sensitivity means more noise is needed for protection. Second, privacy parameter, epsilon. Intuitively, you can understand it as the strength of privacy protection. Epsilon is a key measure of privacy strength. Right? So a lower epsilon means stronger privacy because it adds more noise, making it harder to distinguish individual data points. However, this also reduces data accuracy, so there's a trade-off between privacy and utility. It's negatively related to noise. Smaller epsilon means more noise, while larger epsilon means less noise. And then spread B of the Precision distribution determines how widely the noise is distributed, as is calculated as F, global sensitivity, divided by epsilon, privacy parameter. So a small b results in a narrow Tor distribution, meaning noise is tightly concentrated around zero. A larger b results in short, wider distribution, meaning noise is more spread out, increasing privacy but reducing accuracy. These parameters work together to control the balance between privacy and then the data utility in differential privacy. A well-chosen epsilon ensures that individual data remains protected while still allowing useful insight to be drawn from the dataset. Understanding and adjusting these parameters is key to implementing effective differential privacy. So one of the key techniques for ensuring differential privacy is the Laplace mechanism. This method helps protect individuals' data by adding random noise to computation, ensuring that private information remains secure while still allowing meaningful data analysis. The Laplace mechanism achieves differential privacy by adding noise to the output of computations, such as sums, means, and machine learning predictions. The amount of noise added is controlled by the privacy parameter epsilon that we discussed. So the Laplace distribution is ideal for privacy protection because it has heavy tails, meaning it occasionally adds larger noise values than a normal Gaussian distribution. This makes it harder to infer individual data points from statistical outputs and improve privacy protection. So the Laplace mechanism is used in places like statistical analysis, such as protecting privacy in computations like mean, sum, and count. It's also used in machine learning and data sharing. In machine learning, it's used to ensure private models by adding noise to training process. And for data sharing, it allows organizations to share anonymized dataset while preserving privacy. So the Laplace mechanism is a fundamental tool in differential privacy. And by balancing the trade-off between data utility and privacy protection, it's widely used in data analysis, machine learning, and secure data sharing. And it makes privacy preserving computations possible in real-world applications. Next, let's look at the Laplace distribution. It's a probability distribution commonly used in differential privacy to add noise to data. It plays a key role in ensuring that individual records remain unidentifiable while allowing useful data analysis. So here I include the probability density function, PDF, of Laplace distribution. And mu here is the location parameter, which determines the center of the distribution. B is the scale parameter, which controls the spread of the distribution. And X is the random variable, taking value in negative infinity to infinity. So key characteristics of the Laplace distribution include its symmetric. It has symmetric shape. So the distribution is centered around mu, meaning it's equally likely to produce positive and negative noise values. And it has sharp peak and heavy tails. The PDF has a sharp peak at the mu and decays exponentially as x moves away from mu. And due to its heavy tails, the Laplace distribution generates larger noise values compared to the Gaussian or normal distribution with the same scale parameter. So the Laplace distribution is used in differential privacy for multiple reasons. I have already discussed some of them in previous slides. So first, it ensures that the noise added is sufficient to obscure individual data points, making it harder to infer the sensitive information. It balances privacy and data utility by protecting individuals while maintaining useful analytical insights. And it's widely used in privacy-preserving computations, such as querying datasets, machine learning models, and statistical analysis. So the press distribution is essential for achieving differential privacy. Its ability to generate controlled yet varied noise helps prevent re-identification while ensuring data remains useful for analysis. Understanding its property allows for better implementation of privacy-preserving techniques in real-world applications. So privacy concerns are growing in the digital age, and many individuals worry about how their data is used. Local differential privacy, or LDP, offers a solution by introducing plausible deniability, which is the ability for individuals to deny that their personal data contribute to an analysis. So again, plausible deniability refers to a situation where an individual can deny involvement in an action or communication because there's no concrete evidence linking them to it. In the context of data privacy, this means individuals can claim that the data was not used in a specific analysis because of added noise. So unlike traditional differential privacy, which add noise after data collection, local differential privacy adds noise before the data leaves the user's device. This means each person randomizes their own data before it's sent for analysis, making it difficult to trace specific responses back to individuals. As a result, even if a dataset is leaked or analyzed, individual contributions remain obscured, giving users a layer of protection and plausible deniability. So it's important to have this local differential privacy and the resulting plausible deniability, because multiple benefits can be derived from this approach. First, users can deny specific data usage, meaning if data is leaked or used for unexpected purposes, individuals can claim their data was not part of it due to the added noise. And second, it enhances trust. People are more likely to share data if they feel their privacy is protected. Therefore, strengthen relationships between users and organizations. And it protects against misuses. Individuals who fear their data being used in harmful way can benefit from this added layer of security. And there are limitations of local differential privacy. First, there's no full proof. If an attacker has access to external data sources that were not protected by LDP, they may still identify individuals. And too much noise reduces data utility. If too much randomness is added, the data becomes less useful for analysis. Balancing privacy and accuracy is crucial here. Therefore, local differential privacy is a powerful tool that not only enhances privacy protection, but also provides users with plausible deniability. While it's not a perfect solution, it helps bridging the gap between data analysis and user privacy, making it a valuable approach in today's data-driven world. So how can we collect truthful data on sensitive topics while protecting individual privacy? The randomized response techniques offers a solution by introducing randomness into responses, ensuring that individual answers remain private while still allowing useful data analysis. So first, let's look at how randomized response works. Imagine a researcher asks a sensitive question such as, have you ever used illegal drugs? Instead of answering directly, the individual flips a coin. If head, they answer truthfully. If tails, they respond yes or no at random, regardless of the truth. So this process masks the true response, making it impossible to determine if an individual is telling the truth or responding randomly. So we use randomized response for mostly for three purposes. First, it protects individual privacy. Since responses contain random noise, no single person can be identified. Second, it creates plausible deniability. An individual can always claim their response was randomly generated. Third, it still allows useful statistical analysis. While individual responses are unreliable, aggregate trends can be inferred using probability formula. So how do we estimate true proportions? Although individual answers are noisy, the overall proportion of yes responses in a large data set can be estimated mathematically using the formula p hat equals to 2a minus 1/2. So here a is observed percentage of yes responses, so something that we can get from data. P hat is estimated percentage of people who truly answered yes, so this latent that we try to estimate. So this formula helps researchers uncover real trends while preserving individual privacy. So local differential privacy that LDP we discussed in previous slides extends this concept by introducing multiple levels of randomization. Instead of flipping a single coin, we can use multiple randomization steps, and additional random noise can be added to responses for even stronger privacy. So the randomized response technique is a simple yet powerful privacy preserving method. It enables data collection on sensitive topics while ensuring individual responses remain private. When combined with local differential privacy, it becomes even more robust, helping balance data utility and personal privacy in real-world applications.